Dengan saya
Dengar, okey.
Ya, dengar.
Saya dah rekod Okay. Ni 11 kV lah masuk. 11 kV. Tengoklah ada apa dekat dia punya panel ni. Oh, mesti pelik kenapa ada heater kat situ. Dan tiap-tiap bilik substation ni mesti ada ni single line diagram. Okey, ni yang lepas bilik 11 kV ni. Okey, protection kat situ, yang ni lah satu circuit breaker, vacuum circuit breaker. Ini gambar yang dulu saya pernah tunjuk. Kabel akan masuk dari bawah tanah. Ini gambar dari bawah tanah. Masa saya ambil gambar ni, dia tengah nak tukar circuit breaker tu. Sebab circuit breaker tu pernah tak berfungsi dan terbakar. Jadi tukar yang lain. Okey, gambar sekarang ni adalah gambar dalam transformer. Okey. Gambar dalam transformer. Transformer ni ada casing kat luar. Ini casing dia yang besar ni. Warna putih ni. Dan tunjuk suhu sekali. Yang transformer ni ialah dry transformer. Tak ada oil. Kalau oil tak nampak dalam macam ni. Ni dry. Satu primary, satu belah sana secondary. Capacity 2500 kVA. Tengok ada tulis TX2. Ni transformer nombor 2. Jadi kita ada dua transformer. Satu line backup. Okey. Okay, gambar yang pertama tadi. Gambar yang pertama, mana pertama? Ni di bilik low voltage. Lepas transformer, kita step down ke 415. Di transformer step down 11 to 415 volt. 11 kV to 415 volt. Bilik ni 415 volt untuk distribution. Main switchboard. Tengok dekat yang saya highlight ni ialah air circuit breaker. Okay, air circuit breaker dipakai pada 415 volt. Ada yang nak tanya ke? Saya dengar tak dengar suara awak. Lag. Kalau ada boleh type lah. 630 M. Apa tu? Kenapa 630? Awak tengok kat mana 630? Ni air circuit breaker ni. 415 volt. Yang ni pula ialah capacitor bank. Okay, dalam casing banyak-banyak ni, ada yang kanan sekali tu, yang hujung sini, bawah ni ada capacitor bank. Capacitor bank dan transformer bank. Okay. Dia ada bentuk, ada nilai-nilai tertentu lah. Dan di luar capacitor bank punya casing tu, ada benda macam ni. Ada lampu-lampu macam ni. Okay. Capacitor unit apa? Unit untuk capacitor. Lupa dah. Unit untuk capacitor.
Farad.
Okey. Jadi untuk capacitor bank unit dia apa? Capacitor bank.
kilofarad.
Kilofarad. Awak dah lupa subjek EPS. Awak kira capacitor bank punya correction. Unit apa waktu tu? Tak ingat dah. Tu depan mata je. Saya tengah tunjuk gambar. Kan? Tu.
Microfarad.
Cik Muhammad Asad Safwan. Keva tu. Tu ada depan kan? Dalam gambar tu. Jadi tiap-tiap capacitor bank tu nilai dia bukan nilai yang spesifik. Kalau kita kira kita perlukan contohnya 30 keva. Tak ada nilai 30 keva kat sini. Sistem akan pilih yang mana terdekat dan yang lebih besar. Ni. Tengok ni. Yang ada capacitor bank, ingat step 1, step 2, step 3. Nanti benda ni akan bertambah bertambah ataupun dia switch yang mana perlu join dengan yang mana. Contohnya 25 campur dengan 50. Contoh 100 campur dengan 25 contoh. Dia akan sistem akan buat macam tu. Okay. Jadi capacitor band tu yang ada dalam ni adalah satu capacitor band tu 25 kV. Yang lain pula 50. Ada yang 100 kV. Jadi sistem akan atur lah benda tu. Kalau power factor bawah nilai yang tak kena, yang nilai yang tak bagus lah. Nilai yang tak bagus ni bawah 0.85. Okay. Dia mesti lebih pada tu. Kalau power factor jatuh bawah tu, jatuh bawah 0.85, 0.6. Jadi sistem akan kira dan dia akan top up dengan kapasitor ni. Okay, dia akan on kapasitor nilai-nilai tertentu. Jadi supaya lebih, supaya power factor naik lebih 0.85. Okay, kalau power factor pun tak ingat, awak mundur baliklah kelas lagi ambil EPS ke, tengok balik nota. Maksudnya tahun 4 tak ada masalah lah. Okay, tadi ada yang sebut VCB 630 ohm M. Kenapa? Ada tulis kat situ ke? 630. Kat mana awak tengok? Rated amps. Dia punya rated amps 630. Rated dia, rated current. Okay. Jadi apa dia tunjuk? Okay. Jadi kita sambunglah kelas kita. Hari ni tak panjang untuk habiskan chapter 2 ni. Oh, ramai lah ni. 49. Okay, kita akan sambung. Last kali kita habis dekat switch gear. Gambar tak keluar gambar ni. Habis dekat switch gear. Jadi kita akan mula dengan arc voltage. Arc voltage ni ialah voltage waktu kita buka contact. Moving contact terpisah daripada fixed contact dalam circuit breaker akan ada arc. Okay, akan ada arcing. Okay. Okay. Jadi apa? Macam mana kalau kita ambil osiloskop, kita nak tengok bentuk dia. Macam mana sebenarnya bentuk arc voltage ni. Okay. Buat dia macam dalam figure ni. Okay. Yang ni, yang macam beralun ni. Ini rupa dia. Okay, the voltage drop across the arc is called arc voltage. Okay, kalau kita measure voltage antara arc tu, itulah arc voltage. Arc path is purely resistive. Okay, sebab apa resistive? Sebab current, sebab arcing tu sendiri ialah terdiri daripada plasma. Plasma ni ialah molekul yang dah terpisah. Okay, dia jadi ion yang bergerak. Jadi bila ada pergerakan ion, maksudnya sepanjang laluan tu ialah resistif lah. Dia boleh bergerak. Charge boleh bergerak. Okay. Sebenarnya dia in phase with short circuit current. Okay, voltage ni dia in phase sama dengan short circuit current. Tak ada phase shifting. Okay, dia sama phase. Very low arc voltage magnitude, only a few percent of rated voltage. arc interruption obtained by separating two contact in a medium, for example SFC ataupun oil dan vacuum. Jadi macam mana arc interruption tu, proses tu berlaku? Ada dua proses di sini. Nombor satu, kita boleh terangkan dengan high resistance interruption, dan nombor dua ialah current zero interruption. Okay, so inside current zero interruption, there are two theory that can be used to explain this one: recovery rate theory and energy balance theory. Okay, let's take at high resistance interruption first. Okay, is resistance increase. Okay, it's refer to arc. Okay, the arc, the plasma is to reduce the current to a significant to a value insufficient to maintain the arc. Cooling by cooling or lengthening, constraining, and splitting the arc. Okay, this is how the resistance is increased. There depends on different types of circuit breaker. Yang ada minyak dia akan boleh cooling ataupun constraining, lengthening bila kita open open the contact. Okay, so the arc will be lengthened. And some circuit breaker split the arc by, for example, flowing SFC, the SFC gas, or high speed air, okay, high speed air, so that when the, can imagine this is the arc between these two contact, okay, then air will be blow, maybe from bottom or from the above, okay, opposed to the location of the splitter. Okay, splitter usually like this, is like knife, so the arc will be suppressed to the splitter, and it will follow the root of the splitter, so that it will lengthen its length. Okay, will be lengthened further, so that the resistance will be increased, and then the current will stop to flow. Okay, when current is interrupted, the energy associated with its magnetic field appears in the form of electrostatic energy. High voltage remain across the contact of CB, of circuit breaker. If voltage larger than withstanding capacity of the gap between the contact, the arc will strike again. Okay, if the voltage is high enough, so arcing will strike again. Okay, so we will discuss further in high voltage section about this one. Why high voltage will restrike the arc. Okay, will reproduce the arc. Not suitable for large current interruption, suitable for low current AC and DC circuit breaker. Current zero interruption. Okay, this is the second type of current arc interruption, applicable for AC circuit breaker. The current waveform will cross 0 point every half cycle or 100 times per second at 50 Hz. For arc interruption, the current will not interrupt at any point other than the 0 point. Otherwise, a high transition voltage will occur across the contact gap. The current is not allowed to rise again after zero current occurs. So what will happen here is the circuit breaker will only interrupt the current. Okay, the circuit will open the circuit only at when the sinusoidal wave cross zero. So voltage becomes zero, current becomes zero. Okay, Okay, this is how it works for this current zero interruption. So there are two theories to explain this type of interaction. The first one is recovery rate theory or recombination rate theory. Okay, so what happened here is, as I explained before, the arc itself is a plasma, which is instead of ionized gas. Okay, the gas is contained of ions. Okay, electrons, a positive and negative ion, or positive ions. Okay, electrons or negative ions and positive ions. Okay, so we need to remove that component immediately after the current reaches a natural zero, zero voltage or zero current, by recombining them into neutral molecules, sweeping them by inserting insulating medium. So this is what I explained earlier, where when during the open contact, okay, the arc is between the contact, okay, so we blow an insulating gas or maybe oil, okay, or high speed air blast circuit breaker air blast, so that we can sweep, okay, sweep all the ionized gas, all the ions and including electrons, okay, and then it will recombine between them. Positive and negative will recombine, become neutral molecules. Okay, this is recovery rate theory. So the arc is interrupted if ions are removed at a rate faster than rate of ionization. Okay, we need to make sure, okay, the removing rate is faster than the ionization rate. Okay, the rate of dielectric strength of gap recovers is compared with transient voltage across the gap rises. If increment of dielectric strength is larger than transient voltage, the arcs will extinguish. If else, the ionization persists and breakdown of the gap occurs, resulting arc for another cycle of life. Okay, we must make sure we can remove it faster by maybe blowing high speed air or blowing SF6 gas. Okay, if you have any question, you can ask. Okay, the second one is energy balance theory. Energy is generated in the space between the contacts after arcing. Energy in the form of heat due to rise of striking voltage and current at the contact. CB is designed to remove this generated heat, okay, which is a form of energy, by cooling the gap, either by blowing air blast, okay, a high speed air, or oil, okay, at high velocity and pressure. Okay, if the rate of removal of heat is faster than the rate of heat generation, then the arc can be extinguished. Okay, so we need to cools down the contact as fast as possible, so that the arc can be extinguished. Okay. If the rate of heat generation is faster than heat dissipation, then the breakdown or the generation of arc will occur again. Okay, so in these two theory, this recovery rate theory and energy balance theory, only works in during current zero current and zero voltage. Okay. Okay, now let's take a look on restriking voltage. The arc is extinguished at the instant of current zero. The voltage across contact will oscillate as transient condition. The striking voltage is the transient voltage across the breaker contact at the instant of arc being extinguished. Okay, so you can see from this figure. This is the restriking voltage if the second cycle of the arc to occur again. And the recovery voltage is voltage across the gap after the arc is fully extinguished and transient oscillations disappear. Okay, so at this recovery voltage, no more arcing. Rating of circuit breaker. To open the contact to clear the fault, to close the contact onto a fault, to carry fault current for a short time while another circuit breaker is clearing the fault. So for circuit breaker, this is the rating that we use: breaking capacity, making capacity, or short time capacity. So what is breaking capacity? It is this circuit breaker capability of breaking under specified condition of recovery voltage. There are two types of breaking capacity. Okay, the first one is symmetrical breaking capacity, which is the RMS value of fault current or AC component. And the second one is asymmetrical breaking capacity, which is the value of total current comprising both AC and DC components. Okay, symmetrical only consider AC component, and asymmetrical involve AC and DC components. Means that, for example, the cycle is 200 11 kV, for example, 11 kV maximum voltage and minimum negative 11 kV. So if it has DC component, maybe it can shift up or shift down. Okay, above. Means that 11 kV, maybe if it has 5 kV of DC component, it will go up. Okay, making it to 16 kilovolt. Okay, and the lower value becomes minus 6 kilovolt. The breaking capacity is expressed in MVA. Okay, as you can see here, this figure shows two components. The first one asymmetrical. Here, you can see the voltage is shifted up. Okay, so it's not symmetry. And this one is symmetry. Symmetry means that the voltage of positive and negative cycle is same. This one is not symmetrical. Like I said before, maybe this one is already 16 kilovolt due to the DC component, and the lower part becomes negative 6 kilovolt. So it's not symmetry. Okay, this is how to calculate the breaking capacity. √3 times the rated voltage in kV times the rated current in kilo amp. Ini salah tulis ni, K ni kecil. Okay, the rated asymmetrical breaking current is 1.6 times the rated asymmetrical current. Okay, and this is another illustration to show the difference between the symmetrical and asymmetrical components. The next is making capacity. which is the peak current in the first cycle of a circuit breaker when it is closed on short circuit. The capacity depends on its ability to withstand the effect of electromagnetic force. Okay, as written here is the how to calculate the making current and making capacity. Short time current rating. Short time current rating is the RMS value of current that the CB can safely operate for a specific short period. Thermal and mechanical limitation is also taken into account. A CB must be capable of carrying the short circuit current for a short period, while another CB in series is clearing the fault. Okay, next is the definition of rated voltage, current, and frequency. Rated voltage is the maximum voltage that the CB can carry continuously. Maximum voltage. Okay. Rated current is the RMS current that CB can carry continuously. And rated frequency is frequency of the CB that has been designed to operate. Okay, for switchgear panel rating, MV switchgear panels are rated based on following specification. Nominal voltage, for example, 11 kilovolt. So it's difficult to maintain the 11 kilovolt due to difference, a lot of due to various number of load. Okay, so the actual voltage will fluctuate between 10.5 to 11.5 kV, means that 5% okay, of the nominal voltage. So what is rated voltage? Voltage level at which the equipment will be expected to perform under normal operating condition. Rated voltage will determine the insulation properties of the each component, CB, bus, cable termination, etc. must be rated to this voltage or higher. Normal practice of rated voltage at switchgear is 10% higher the nominal voltage. This explanation on fault current. Okay, how do we determine the fault current in a system? The first one, there are a few assumptions that we can use. Okay, the first one is assume fault occurs very close to the switchgear. Cable impedance between switchgear and the fault may be ignored. Okay, switchgear, fault, very close. So we can ignore. Okay, due to the short distance between this fault location and the switchgear. Okay, so that we can ignore. Ignore arc resistance. Okay, if we consider arc is a conductor must have at least very little resistance, but we can ignore in the system. Then in the calculation, ignore cable impedance between transformer secondary and the switchgear. Okay, between transformer secondary and switchgear, because between that is also we have cables, so we ignore. Okay, ignore the impedance. When adding cable impedance, assume the phase angle between cable impedance and transformer reactance is 0. Then ignore complex algebra and use readily available from cable manufacturing. Okay, let's take a look on the example. Okay, the first one is by ignoring cable impedance. For example, we have a transformer rating. Primary voltage is 132 kilovolt, secondary 11. So it's a step down transformer. 132 to 11 kV. The capacity is 200 MVA, and impedance of the transformer is 0.1 or 10%, 0.1 pu. Okay, so how we can calculate this fault current? Okay, firstly we need to determine the impedance of the transformer. Okay, by using this equation, S equals to V squared over Z. Okay, so refer to secondary side of the transformer. So V secondary is 11 kV. Okay, if we refer to secondary side, so 11 kV square over 20 mega VA. Okay, so we get 6.05 ohm. Okay, in order to get the actual, ZB is base value. Okay, if you forget about this, you can refer to EPS notes, electrical power system. Okay, so Z actual equals to ZPU times the Z base. Okay, PU is in percent here. So just multiply 0.1 to 6.05 ohms, and we get 0.65 ohm. Okay, then we can calculate, we can determine the fault current, which is Vs over square root 3 times Z actual. So all the value is available here. We can just use the value and get the fault current is 10496 amperes. Okay, a little note here. If more than one transformer is connected in parallel, for example, 2 transformer, so we need to multiply by 2. Okay, like what happened in our substation, what I showed you just now. We have 2 transformers, so we need to multiply by 2, and we get the fault current for 2 transformer. Okay, second example with cable impedance. Okay, just now we ignore the cable impedance. Now we consider cable impedance. When the switchgear located quite a distance from the transformer, we need to take into account, into our consideration, the impedance of the cable. Okay, for example, here the cable length is 6 km. Okay, 6 km. Okay, and this is the type of cable and its insulation. And we have size of the cables, current ratings, impedance per kilometer. 4 cables are installed in parallel between transformers and switchgear to achieve the required current rating. So here we already calculated from example 1. It's similar, same transformer. So Z transformer is already calculated. Okay, due to the parallel configuration of the transformer, this is basic circuit analysis, maybe basic physics. You should be able to calculate this parallel impedance value. Okay, So times 6 for 6 km, and we get the cable's impedance 0.2322 ohms. So total, just add Z transformer and Z cable, we get Z total. And then use same formula to calculate the fault current. Okay, so we use Z total here and put it here. We get 7,586 amps. So if two transformers are fed in parallel to the switchboard, just multiply. Okay, multiply the value, multiply this value by fault, and you will get this value. Usually for current rating will be specified as a current and time. Okay, meaning current can flow for how long? For example, here is 20 kiloamps for 1 second. So what does it mean? It means that 20 kiloamps current can flow continuously for only 1 second. Okay, just a little calculation. Okay, this is what I showed you just now in the beginning of this class. This is very old switch gear. You can see the meter here is analog. Okay, so this is switch gear. Okay, it consists of a lot of things. Okay, circuit breaker, switch, disconnecting switch, bus, measuring instrument, and relays, associated device. Okay, and enclosed in this metal cabinet. Okay. Okay. So that's all for today. We finish our chapter 2. I will open a quiz for chapter 1 and chapter 2 in Kalam. I will inform you in the group later. Okay, any question? I want to stop here.
When
Yeah.
the quiz, sir? When will be the quiz, sir?
Quiz, I will inform later in the group.
Okay, sir.
Okay. So next week we will start chapter 3, yeah. Okay, guys, we end our class here with tasbih para surat Al-As. You may dismiss.